Hi, this is Fiona French, and today I'll be discussing Lab 3, the black hole. Here's the table of contents, including the introduction, fundamental principles, Part 1, mass of the black hole and the computational model, Part 2, don't crash the computational model, sources of error and discussion questions. This lab is composed of two parts. In Part 1, the main objective is to estimate the average mass of a black hole by simulating the interaction between the motion of a star of known mass and a black hole with net forces present. In Part 2, we wanted to determine the initial velocity that a spaceship must have to escape the surface of a planet without crashing or entering the black hole. We will be applying the momentum principle, saying that a change in momentum is equal to the net force times change in time. When written in terms of magnitude and direction, the derivative with respect to time can be taken, which allows us to break dp over dt into parallel and perpendicular components. Thus, when taking the sum of these two components, the output will be the net force. A change in direction will correlate with the perpendicular component, whereas the change in speed will correlate with the parallel components. We'll also be applying the velocity and position update formulas. We will also be utilizing law of universal gravitation, which describes the attractive force between two objects to calculate the mass of the black hole. This is proportional to mass and inversely proportional to the distance between centers. Force of gravity equals g times m1 times m2 over r squared times r hat. This can also be rewritten in terms of momentum and rearranged to isolate mass 2, which will give us the mass of the black hole. The main results of this lab include the mass of the black hole being 8.25 times 10 to the 33 kilograms, F net being 8.06 times 10 to the 28th power newtons, F parallel being 2.97 times 10 to the 28th newtons, and F perpendicular being 7.51 times 10 to the 28th newtons. In Part 1, mass of the black hole, the system includes the black hole and the surroundings where everything else, including the star. Initial conditions were inputted, including the star's mass, the amount of time, which was 1 day converted into seconds, and the observation time equaling 0. In this computational model, our ultimate goal is to find the mass of the black hole, thus we need to calculate the change in momentum as the star orbits the system at multiple instances. These lines of code include various equations to calculate parallel and perpendicular components of momentum. The final line shows the rearranged equation where the mass of the black hole equals the magnitude over change in time times the radius squared all over g times the mass of the star. We had to edit the arrow scale in our animation, which will be shown on the next slide. Here's the animation of the star recoded, showing it orbiting the black hole. In Part 2, don't crash, the system includes the spaceship and the surroundings where everything else, including the black hole and planet. We inputted the initial conditions, including the mass of the black hole calculated from Part 1, and the mass of the planet and the mass of the spaceship. Wanting to find the initial velocity the spaceship must be traveling to not collide with the black hole or planet, we built a computational model where we had to guess and check inputs for the initial velocity with the x and y direction. The code includes various equations where we were calculating the net forces acting on the spaceship from the black hole and the planet. After lots of trial and error, I found that the initial velocity was negative 3.10 times 10 to the 7th power in the x direction and 2.76 times 10 to the 6th power in the y direction in meters per second. And the closest distance between the spaceship and the black hole was 9.91 times 10 to the 10th power meters. Here's the video of the code that shows the spaceship successfully leaving without running into the planet or the black hole. A note that should be made is due to the experiment being purely computational, there's no graphical comparison between real-world data and computational models. There may have been multiple sources of uncertainty during this experiment. Starting with Part 1, when running the code, we were given a rate to choose. The start code was set to 50 iterations by change to 150 from my data, but the greater the time interval, the more accurate the mass of the black hole will be due to it being an average from many instantaneous points in time. Additionally, running the mass would affect the data. In Part 2, the initial velocity was estimated via guess and check method, and any errors in Part 1 would directly affect the results of Part 2 because the mass of the black hole was in the initial conditions. Overall, in Part 1 and Part 2, the computational model does not take into account any external forces that may have been acting on the system other than the net force of the planet and the black hole on the system. There's a high probability that in reality there are various stars, planets, and asteroids in the universe that would affect the net force. So what does this mean, and how are the net forces, parallel and perpendicular components different from the rate of change in momentum of parallel and perpendicular components? So the net force is equal to the change in momentum over time, so we know that the net force describes the force acting on the system, and dp over dt describes how momentum is changing. The parallel components of the net force and momentum are actually equal, as are the perpendicular components of the net force and the change in momentum due to Newton's second law mathematically. However, they are the same values, however the complexity varies in solving. It's much easier to solve for the change in momentum. The net force is much more difficult because you have to compute and account for all the forces acting on the system, but for the change in momentum, all you need to know is the system's change in velocity and motion. So then what if? What if you wanted to orbit the black hole instead of escaping? So via trial and error again, I computed the initial speed that you would need in the x and y directions. So I found that it was negative 0.6 times 10 to the 5th power in the x direction, and then 7.9 times 10 to the 6th power in the y direction in meters per second, and then the purple circle actually shows it orbiting the black hole.